This is part 2 of the redox reactions notes. In part 1, we briefly talked about what is a redox reaction and how do we assign oxidation numbers. In this video, we are going to write redox half reactions. So redox reactions, reduction and oxidation happen simultaneously. And remember that reduction is the first part of that name. Oxidation is the second part of that name. And so in a redox reaction, one element is going to be oxidized, meaning that it loses electrons, and one element is going to be reduced, meaning that it's going to gain electrons. And so we're going to see that oxidation number increasing if electrons are lost, because that charge is going to become more positive. We're going to see one oxidation number decreasing, because again, you're gaining electrons, the charge is going to become more negative. And each of these is called a half reaction because each makes up half of the full redox reaction. Some examples of what these half reactions look like. This is an example of an oxidation reaction. Notice we only have zinc in this, so zinc is our element that's being oxidized. So zinc has less electrons after the reaction. So we've got neutral zinc, and then after the reaction we have zinc with a +2 charge, and it lost 2 electrons to something else, to some other element in our reaction. We don't care where those went, we just care that they were lost from zinc. In a reduction reaction, for this example, copper has more electrons after the reaction. So we have copper with a +2 charge, and copper is going to gain electrons from something at the start of the reaction. After, though, copper's charge goes down now, it's becoming less positive, and so it is reduced. It has gained electrons from the start of the reaction to after. Another example is if we have neutral phosphorus, and if it is gaining electrons from something else, then neutral phosphorus would become phosphorus with a -3 charge. So notice the charges going down. This went from charge of 0 to charge of -3. That is still a decrease in charge. So it's with that. So our process for writing out these half reactions, we use what we know about oxidation numbers by assigning oxidation numbers to all of our elements. Then we can determine what is actually having that change in electrons, what is oxidized and what is reduced. Then we pull out the element that's getting oxidized or reduced, and we write the half reaction. And at the end, we need to make sure that our electrons agree in our half reaction, because we can't gain more than we lost. So let's look at this first example. Our first step is going to be to assign oxidation numbers. Magnesium has an oxidation number of 0 when it's by itself. Sulfur, 0. Magnesium is a +2. It's a simple metal. Sulfur is a -2 here. So what is oxidized? Remembering oil rig, oxidation is loss. And so if you are losing electrons, your charge is going to go up and your oxidation number is going to go up. So as we look at this, magnesium had an oxidation number of 0. Now magnesium has an oxidation number of +2. So magnesium was oxidized in this reaction. Reduction is gain. That's the second part of that oil rig. If you are gaining electrons, your charge is going to go down. It will become more negative, and that is what it means to be reduced. So sulfur had a charge of 0. After, sulfur has a charge of -2, and so that is how we are so sulfur is our reduced element here. So now we need to go through, let's write that half reaction. Magnesium, I'm using that oxidation number of 0 as a charge now. Magnesium is going to have a charge of 0. We don't write charges of 0. And then magnesium has a charge of +2 after, so I'm kind of copying down my magnesiums on the side of the reaction that they started with. But because we're talking about electrons, we need to make sure that however many electrons we have at the start is what we have at the end. If I reference my periodic table and I find magnesium, magnesium has 12 electrons when it is neutral, If magnesium has a +2 charge, that means that it has 10 electrons. Well, where did those electrons go? They were, oxidation is loss. They were lost to something else. And we can see that they're lost to this sulfur up here, but in our half reaction, we don't care what they were lost to. We just need to show those. And so now I can, so that is my half reaction. And I put my 2 electrons here because I had 12, and then that needs to equal 10 plus another 2, so 12 electrons total. For our sulfur half reaction, now I am writing down my sulfur, so sulfur and then sulfur with a -2 charge. If you're not sure what side your electrons go on, I did sulfur with a 0 charge here because of that oxidation number of 0, sulfur with a -2 charge here because of that oxidation number of -2. If you're not sure where those go, let's look at our periodic table. Sulfur has 16 electrons when it's neutral. If sulfur has a -2 charge, that means it's going to have 2 more, 18 electrons. We can't have 16 on one side and 18 on another. So that means we're going to have 2 electrons, so +2 electrons on the left to get that total of 18 on each side. That last step, make sure the number of electrons agree in each half reaction. And so we can't lose more than we gain. So then our last step is making sure that we have the same number of electrons here. We do both of them because both of those had a charge of 2. The number of electrons agrees, and so we don't have to do any editing to our reaction. All right, let's do another one. Magnesium is going to have an oxidation number of 0, hydrogen +1, chlorine -1, magnesium +2, chlorine -1, hydrogen 0, because it's a free element. Feel free to pause the video and take a little more time to think about those. Oxidation is loss. If you're losing electrons, your oxidation number is going to go up. Reduction is gain. If you are being reduced, your oxidation number is going to go down. So let's look at comparing. We've got magnesium with a 0 oxidation number at the start, magnesium with a +2. Well, 0 to +2, that means that magnesium was oxidized. Looking at our next element, I've got my hydrogen is a +1. Then after hydrogen is a 0, well, +1 down to 0, that's showing reduction. And then whatever else we have, we should only have one thing that's oxidized, one thing that's reduced. Anything else that's left should not have any change. So chlorine started with a -1 and it's ending with a -1. Notice it's paired in both of these. So it is gaining electrons in each of its compounds, but it doesn't change how many electrons it has from the start of the reaction to after. So now that we've determined this, let's go through and write our half reactions. So I'm pulling out those pieces from magnesium up above. Magnesium has a charge of 0 on the left. Magnesium has a charge of +2 on the right. And with this, now thinking, well, where are my electrons going to go? Well, if magnesium has a +2 charge, oxidation is lost. That means that after our reaction, that magnesium's 2 electrons went somewhere, that somewhere being chlorine. And so that's our oxidation half reaction. For our reduction half reaction, we're going and pulling what we have for our hydrogens. We've got hydrogen with a +1. This one is a little tricky though because we can't just have a hydrogen by itself, so that means that this is it's an H2, which then means we can't have 2 hydrogens on the right and 1 hydrogen on the left. So we do actually need a 2 here for that coefficient. You'll notice there is that coefficient in front of our 2 from the original reaction, and so it is there for a reason. And so we do need that. So if you end up with a diatomic, which we don't often, you do need to put a 2 in front of that hydrogen +1 ion. And then looking at how do we get those electrons to match? Well, your electrons are generally going to go on the side that with a positive charge. And if we just did +1 electron in here, that's not going to take into account that we have those 2 +1s. So we actually need 2 +1s, 2 electrons are needed in our half reaction, like that. And then that fixes any potential problems we might have of making sure the number of electrons that we have agrees. We have 2 electrons in each of our half reactions, and so those are the electrons that we need to agree, along with our electron numbers staying consistent from before to after our reaction. All right, on to our next one. I'm just going to write down my oxidation numbers. Feel free to take time to do this on your own more slowly and think through them. Oxidation, that means our oxidation number is going to go up. As I look at that, sodium starts with 0, ends with +1, and so sodium is oxidized. What is reduced? We've got iron starting at +2, ending at 0. The oxidation numbers went down, and so iron was reduced. Going through and writing my oxidation half reaction, I'm going to pull out my sodium. Sodium with a charge of 0. That's coming from here. And then our sodium with a +1 from there. And then making this a neutral, or making sure we show those electrons being transferred. Sodium, and then sodium +1. Well, if sodium has a +1 charge, that means that one electron was lost to something else. And so here's my half reaction for my oxidation. Looking at my reduction, pulling out our iron, I've got iron with a +2. And then after, I've got my neutral iron. Where are those electrons going to go? Well, if we have, those electrons generally go on the side with our positive, so +2 electrons there, because if this is a +2, we need 2 electrons to get to that neutral. And so there's my reduction half reaction. Now that last part, that step where we've had to check to make sure they match, making sure our number of electrons agree, well, now that's when we're looking at the electrons we have here. I only have 1 electron in my oxidation reaction, but I have 2 electrons in my reduction reaction. I need to get these to agree. I can do that by multiplying my entire oxidation half reaction by 2 in order to get this up to 2 electrons. And so in order to do that, we are going to multiply by 2. I'm going to need 2 sodiums, 2 sodium +1s, plus 2 electrons, and now those electrons agree. One thing you might notice is that we already had those 2s in our reaction in order to balance it. And so if you notice it, you might be putting that 2 in right away, but then know that 2 times that +1, you need 2 electrons then in order for our electrons to stay balanced from our start to our end. In example 4, we are going to assign our oxidation numbers. We have a polyatomic here, so we can use that to find the oxidation number for silver. This grouping needs to have a charge of -1 or an oxidation number of -1, so that's going to tell us that silver is going to have a +1 charge. Silver is also a transition metal that always has a +1 charge, so you might recognize that. Then from there, we can assign our oxidation number for oxygen. Oxygen is a -2. If we have 3 oxygens, though, that is a total of -6. Well, -6 and what gives me -1? My nitrogen is going to have a +5 oxidation number. And I see that nitrate group on both sides. So once I found that that's a +5 and a -2, that's going to stay consistent throughout the reaction. My copper is by itself, so that has an oxidation number of 0. Now, when I'm looking in this group, this copper is going to have an oxidation number of +1, and our silver is by itself, so that has an oxidation number of 0. Feel free to pause and try the rest of this problem on your own. Thinking of what's oxidized, remember oxidation is loss of electrons, meaning your oxidation number is going to go up. As I'm looking at these, I have my, and then reduction is gain. So reduced, we're looking at what had oxidation numbers that went down. So looking at my silver, silver starts with a +1 and ends with a 0, and so silver is actually reduced in this case. What is oxidized? Let's keep going. Well, nitrogen started with +5 and ended with +5, so that didn't change. Oxygen started with -2 and ended with -2, so that didn't change. And so then we have copper starts with 0 and ends with +1, so copper is what gets oxidized. Then we're going to go through and pull out those values from our half reaction. On the left, we're just focusing on copper for our oxidized half reaction. We've got copper, and then we have our copper with a +1. Thinking about, well, oxidation is loss, meaning copper from the start to the end, electrons would have had to go somewhere else, and so we will have 1 electron on the right with our copper +1. Also, as a reminder, thinking of your electrons based on your periodic table, where the electron's going to need to go in order for our electrons that we started with to equal the number that we are ending with. Silver is reduced, so now we're pulling silver from that reaction. We've got silver with a +1. On our reactant side, we have neutral silver. On our product side, thinking of how if this is silver with a +1 charge, that's going to have 1 less electron. So that means our electron, +1 electron, is going to go in here in order for our electrons to be equal from our start to end. The last thing that we're going to check, we need to check that our number of electrons agree between our two reactions. And we have 1 electron here, 1 electron here, so the number of electrons agree. Number 5, I've already assigned oxidation numbers. Feel free to try them on your own and then check. So whatever gets oxidized, oxidation is loss of electrons. The oxidation numbers are going to go up, become more positive. And so we see our aluminum goes from 0 to +3. So aluminum is getting oxidized. Whatever is getting reduced, the oxidation numbers will go down. Copper went from 2 to 0, so that copper is what is reduced, and then we can write our half reactions. Pulling now just my aluminum out of my reaction, I've got aluminum neutral. On the left, I've got aluminum with a +3 on the right. How do I get, and so thinking of what side are my electrons going to go on? Well, aluminum with a +3, that means that there are 3 electrons that went somewhere else in order for us to have the same number of electrons as that neutral aluminum. Writing our half reaction for copper. That copper, we have a +2. Copper neutral in our products. Well, copper with a +2 charge, we need 2 electrons from somewhere else that copper +2 is gaining in order to get the same electrons as that neutral copper. Now we go back and do that check. Let's check that the number of electrons in our reaction agree. And as I look at this, I've got 3 electrons in my oxidation half reaction, 2 electrons in my reduction half reaction. So those do not agree, and I need to make it so that those are the same. So how am I going to get this 2 and the 3 to be the same? Well, I'm going to need to multiply my entire oxidation half reaction by something and my entire reduction half reaction by something in order for us to get those electrons to be the same. So I'm going to multiply my entire oxidation half reaction by 2 and my copper half reaction by 3 so that I end up with 2 aluminums produces 2 Al plus 3s plus 2 times 3, 6 electrons, and that is my oxidation half reaction. For my reduction half reaction, I'm going to have 3 copper plus 2s plus 3 times 2, 6 electrons produces those 3 neutral coppers. And now that we have those electrons that agree, those are our final half reactions. One thing you might notice is that we had that 2 aluminum in our balanced reaction. And so if you notice that right away, you might build in those coefficients as you go, the 2 aluminum plus 3s, and then that 2 times plus 3 will tell you how many electrons you need. If you haven't built in those coefficients though, we can add them at the end when we're making sure our number of electrons agree. All right, example 6, I already assigned those oxidation numbers. What is being oxidized is whatever's oxidation number is increasing. Reduced, that number is decreasing. I go through and I check. My copper goes from 0 to plus 1, so copper is getting oxidized. The hydrogen is going from plus 1 to 0, so hydrogen is being reduced. So I can write those half reactions. I have my copper neutral on the reactants. I have my copper with a plus 1 on my products, and then that's going to be plus 1 electron on the side with my copper positive 1. Again, feel free to reference your periodic table looking at how many electrons do each of these have to determine where your electrons need to go. Electrons generally go on the same side of the positives as the positive charge. And then we've got our reduction half reaction, pulling out my hydrogens. I have hydrogen plus 1 over here. I have my H2 over here. I can't have 2 hydrogens on the right and not on the left, so I'm going to put a 2 here. And as I look, my H plus 2, well, I'm going to have 2 hydrogen plus 1s, so I need plus 2 times 1, 2 electrons on the left in order for the electrons before to equal my electrons after. Checking to make sure, do my electrons agree? They do not. This has 2 electrons, this one has 1, so I can multiply my entire copper reaction times 2, 2 coppers producing 2 copper plus 1s, plus 2 electrons, and that is my final half reaction for that. Just like I mentioned in the last problem, if you notice that there are coefficients, you can always build those in, and then that should make it so those electrons match at the very end. At the very beginning of these notes, we talked about how all reactions except double displacement are redox reactions. Use the following 2 reactions and oxidation numbers to explain why double displacement reactions do not meet the criteria to be classified as a redox reaction. Well, in a redox reaction, something has to be reduced and something has to be oxidized. So we use those oxidation numbers in order to determine that. As I look at this, silver is a +1 charge. NO3, this is a -2, which leaves us with nitrogen being a +5. In my sodium chloride, sodium is a +1, chlorine is a -1, silver is a +1, chlorine is a -1, sodium is a +1, and then my NO3, nitrogen's a +5, and oxygen is a -2. So in order for us to have a redox reaction, something has to be reduced, something has to be oxidized. So there needs to be some change in our oxidation numbers. So let's look. Silver is at +1, silver is ending at +1, so there's no change. Nitrogen is at +5, nitrogen's ending at +5, no change. Oxygen is at -2, oxygen's at -2, no change. Nitrogen's at +1, nitrogen's at +1, no change. And same with chlorine, no change. So if there is no change in those oxidation numbers, then it is not a redox reaction. Nothing was reduced, nothing was oxidized in a double displacement reaction. And we can see the same thing as well if you want to practice applying or writing those oxidation numbers, assigning those oxidation numbers in this one. We are also going to see no change in the oxidation numbers from the start to the end of the reaction. Reach out to your teacher with any questions.